But either way. Okay, chapter 9. Chapter 9 is all about NMR. Now, for NMR, just what is it? What does it stand for? Whispers, but I can't hear the whispers, so I have to speak up.
Nuclear magnetic resonance.
Nuclear magnetic resonance. Okay, now we know what it stands for, but what does it do? Specifically, why would we use NMR?
It determines the unique structures of a compound.
Exactly, it gives you the unique structure of compounds. Specifically, it mostly gives you the carbon to hydrogen skeleton, which is really good. So let's just write carbon to hydrogen skeleton. Now, NMR is a spectroscopy tool that we use, okay? Now, IR, it's all the spectrometry tools that we use, but what's IR? What do we do with IR? What does it tell us?
It's like more in depth about methyls, ethyls, alcohols. Yeah.
It's all about functional groups, yes. It just gives you functional groups. So which one do you think is gonna be more specific? NMR or IR? NMR, yes. No. We are gonna learn a new term, which is NMR active. Has anyone read the slides ahead of hand or the book ahead of hand? Any guesses on what's NMR active? Okay, it's the first day, that's okay. You guys can relax. That's completely okay. So NMR active, it just tells you that the the atom has spin states, okay? So let's just start writing this down. Has spin states. Now, that's the normal definition. Now, what it actually means in practice is that you have an odd number of protons, that's the P plus neutrons, or both. Okay? So let's see that in practice. So hydrogen, your normal hydrogen. How many protons does it have? One. How many neutrons? 0. Okay, so in this case, do we have an odd number of protons, neutrons, or both? Yes, so that means that that atom specifically is active. Simple as that. As long as you have at least one odd number, it's active. Simple as that. Now, what about deuterium? Deuterium, how many protons does it have?
One.
It has 1. What about neutrons? 1 as well. Is it active?
Yes.
Yes. Carbon 13, that's an isotope. How many protons and how many neutrons do you see?
6 and 7.
Beautiful. Is it active?
Yes.
Yes. As soon as we see an odd number again, it's automatically active. Now, most of these are gonna be active. Now, how are you guys figuring out the number of protons and neutrons? Quick refresher. We look at the periodic table. In this case, unfortunately, we don't have a periodic table in hand, but hopefully you have one in hand or look it up on your phone too. Now, let's just finish this quickly. Nitrogen 14. Is it active or inactive? Active. How many protons and neutrons?
7.
7 neutrons. Beautiful. Nitrogen 15. Active or inactive? How many protons and neutrons?
7 protons.
Beautiful. Fluorine 19. Active or inactive? Active. How many protons do you see?
9 protons.
Beautiful. Which means you have 10 neutrons. Phosphorus 31. Active or inactive? This one is 15 protons and 16 neutrons. Now let's do one more. Let's do carbon 12. That's the normal carbon. Is that active or inactive? Why inactive?
Because it's six.
It's both, exactly. This one. Inactive. 6 protons and 6 neutrons. Okay, how do we feel about determining if it's NMR active or not? Pretty simple, pretty easy math, that's it. Okay, now, most likely you are not gonna get a question asking you which of the following items is NMR active. That would be a too easy question. So he's not gonna be wasting questions like that. They're gonna be more complex and multiple concepts can be tested at once, okay? Now, NMR, we know 2 different types, at least from Orville 1. What are they?
CNMR,
CNMR, what exactly?
carbon NMR.
What kind of carbon? Carbon 13, there you go. Okay, now, in here, who's taking lab? Do we have you? Lab, has it started or not yet? Not yet? Okay, so this is gonna give you a little advantage. Okay, so I'm not sure if Jermaine ever talked about the solvent that we have to use, but there's a specific feature that it needs to have. Do we know about it? For the solvent?
For the solvents, don't the hydrogens have to be replaced,
Replace with what and why?
deuterium, so it doesn't, show up on the spectrum?
Perfect, exactly. Remember, your solvent is not the thing that you want to test. You're trying to look for a specific molecule. So to make it inactive, we're gonna use some sort of isotope to protect that from being read in the spectrometer. In this case, let's just say anything that's deuterated. So usually it's gonna be CbCl3 or even water, but with deuterium instead. So far, questions on that and why we have to replace normal hydrogens with deuterium? Pretty simple. Okay, we're good. Now, what's gonna be the calibration standard? What's the calibration standard? What does it mean? What are we looking for? Best guess. Best guess.
Is it like a zero?
It's your reference point, exactly. More specifically, it's your 0 reference point. So your 0 ppm value is usually just what's represented by TMS. That's just your reference point. So that means that we use TMS basically to compare the other peaks that we have in a certain molecule. They're all referred back to the TMS. Okay. So far, questions. We're basically just going over concepts. Some are new, some are old. No questions, we're good. Okay. Now, specifically for HNMR, we have 4 different aspects. What are we?
Simplicity,
Simplicity, that's one of them.
integration,
Integration, second.
chemical shift,
Chemical shift. You just count the number of
signals,
unique signals. There you go. So let's just start with number of signals. Okay. Now, how do we know we have a specific number of signals? What are we trying to look for? The peaks,
Same, like they're like in the same group.
they're in the same group, they're exposed to the same thing. So they're basically siblings, okay? So let's just write unique environments. Okay, now, the next easy one is integration. What does integration tell you? And where can you find that in the spectrum? One more time.
Just have them.
Yes, it's under the peak. Now, what does it represent?
Doesn't it represent how many hydrogens are in the same unique segment?
Exactly, simple as that, just how many hydrogens you have per second. So let's just put a number of hydrogens per signal. Now, remember that integration is given in a ratio, meaning that it could be simplified. When could it be simplified? Think about it. When could we simplify the ratio?
Just put it in half.
They're in half.
4 would be 2.
Yes, but when would we simplify it? When you see what in the model? When you see symmetry, exactly. As soon as you see symmetry, you know that it's gonna be simplified. So let's just write symmetry simplifies the ratio. Okay, now, next one. Your chemical shift. What's the chemical shift?
Like it's the placement on the, like, the table, depending on like it's a ketone, it's an alcohol, it's a aldehyde.
It's the specific number that you have at the bottom of the graph, your ppm values. What does ppm stand for? It's per million. Now, do you have to actually remember that? No, you just have to remember the different chemical shifts that we're gonna see. But that's gonna be later on. So for now, chemical shift, ppm value, that's it.
Oh, does Dr. West give the chemical shift chart like Jermaine does during exams or? no?
During exams, no. You guys have to memorize. The only thing you're provided during exams is the periodic table. That's it. Okay, now for chemical shifts, we usually use two different terms. What are they? To describe the positions. I heard de-shielded, shielded. Okay, what do they mean? What's shielded?
It's far away from a functional group.
It's far away from a functional group, it's really protected. What about de-shielded? How do we know something is de-shielded? It has a higher frequency because it's exposed to something that's very electronegative or electron dense. So it's close to an oxygen, let's say. It's close to a triple bond, double bond, those guys. So let's just write de-shielded. This is shielded. And then what's the last aspect that I'm missing there? The names. Multiplicity. But we can also call it, what else? Splitting. Now remember that they mean the same exact thing. Sometimes your professor is gonna use either or, so don't get scared. They're the same exact thing. Okay. Multiplicity splitting. What does it tell you? What is it about?
Like identical groups are next to. It's like the n+1.
It's all about neighbors. Yes, and bless you. And you are correct. This is about the n+1 rule. What does n stand for? What is that?
The number of neighbors.
N, so it shows your neighbor hydrogens. Now, what are some rules for the neighbors? How do we know we have a neighbor? Oops, sorry.
It can't be like cut off, like it has to be, it's like if there's like an oxygen.
You you are going in the right direction. I'll
If
explain.
it's connected to the carbon that's connected to the signal.
Like it has to be like directly connected, like.
Adjacent. It has to be adjacent. Because remember, hydrogens of the same signal, they're siblings of each other, so they can be neighbors of each other, okay? Just remember that. Now, there's a few rules. The one that you were mentioning, it's about heteroatoms. For this class only, you can go past any heteroatoms. So if you have an oxygen right in the middle before continuing the carbon chain, that's a roadblock. You can go past that. So that means that I'm not touching any neighbors. Okay, so heteroatoms. Block neighbors. Now, another rule is that, yes, neighbors have to be adjacent, but there's a max. The max is that your neighbors have to be within 3 bonds. If there are 4 bonds away, that's not a neighbor. If there are 2 bonds away, that is a neighbor, okay? Okay. And has to be within 3 bonds. No, really quickly, for those of you who are taking lab in regards to the heteroatom rule. Sometimes in practice, you're gonna see that you can go past heteroatoms, okay, for multiplicity. You're gonna see that probably later on in the lab, not at the beginning. So just keep that in mind, plus always ask your TAs, okay? Yeah. That's pretty much it for multiplicity / splitting. Now, so far, any questions? Very good. Do we remember those terms? Okay, now, this is for H and MR. The CNMR has also the 4 aspects. Why not? What does it have? It's a unique number of signals, and there's one more. And chemical shift. Exactly. Those are the only ones. You're never gonna see splitting in CNMR. There's no integration. Okay, so keep that in mind. Now, at this point, we know what's the difference between NMR and IR. We know which one could be more helpful and why. Now, we're gonna compare each of those pairs of molecules, and you're gonna tell me what spectrometer would be better, NMR, IR, or maybe both. What about the very first example? Could I use IR to differentiate them? Yes. Could I use NMR? Yes. NMR as well. In this case, both are equally correct. Now, number 2, could I use IR to differentiate them? No IR, why not? What do you notice?
The same functional group is
They're the
present.
same exact functional group. That's all that IR tells you, just functional groups. So if they're not different, spectrum is the same. But what about NMR? That one's gonna be different, so in this case, we use NMR to differentiate them. Now, very last one. Could we also use NMR?
Sorry for the last one, we don't use IR because it's the same functional group is what I heard?
Or 2, yeah.
Yeah.
They both have alcohol, so they're gonna show the same exact data in IR. But for the third one, we said we could use IR, but could we use NMR as well? Or is it gonna show the same exact data? What do we think? We can what?
Say yeah, but.
Is it because
Okay, now,
they have the same carbon skeleton? The only thing that's different is the 2 hydrogens on the nitrogen versus 1 on the oxygen. Would that show?
that is gonna show us very small difference. So technically, yes, you could use NMR. The only difference is gonna be the integration. One of them is gonna be 2H, the other one is gonna be 1H. It's a very small difference, so overall, you could say that you could use NMR, but it's not gonna be the most specific. I would use NMR alongside IR. So let's just write NMR. Specifically HNMR. Okay, so far, questions? Okay, I'm gonna give you a few more minutes to finish writing down your notes.
That's what you said, why can we use NMR in the last one again?
On the last one, you could use NMR because the integration of these two guys is gonna be different. This one is gonna be 2H, this one's gonna be 1H. But again, it's such a small difference that it might not be that helpful. You would have to use both techniques at once.
There's only one hydrogen there, two there.
Because integration is gonna be less because of that.
Because.
Okay, so far. Any other questions? So far, we're good. This is mostly only Orgo 1. We just learned one use thing. Now, before we continue, I'm gonna test you a little bit on your knowledge of Orgo 1. Okay, now, one of the concepts that you're gonna see later on is resonance. Now, it's not gonna be as deep as you saw in Orgo 1. Or resonance. What is it? Why do we do it? Is it a reaction? What is it?
The moving of electrons that stabilizes the molecule.
Now, how do we know we have a major contributor? Not only negative charges, any charges, it's better if they're in something that's electronegative. Now, if you could have one of your resonance forms be neutral, that's gonna be even better. Okay, because it makes it non-reactive, so it's more stable. Now, I think this was on your skills test. SN1, SN2, what kind of reactions are they? Substitutions, good. What about E1, E2? Elimination. Now, addition reactions, what transformation happens in those? You go from what type of molecule to what kind of molecule? Addition reactions, you're adding something. Exactly, alkene to alkane. You're going from double bond to single bond. So you're always adding some sort of hydrogen in the process. Now, let's go back to this little graph in here. This is from your book. Now, let's just clarify some terms in here. Okay, CMS, what was CMS? Your reference point. Okay, now, the part on the left side of the spectrum, is that shielded or de-shielded?
The left side.
Beautiful. How else could we say de-shielded? Non-shielded. So that means that the right side of the spectrum is shielded or unshielded. Okay. In this case, we only have two signals, signal A and B. Okay, now let's look at each one of those. They have little peaks in there. What do those peaks represent?
The hydrogens are on the neighboring carbon.
It's all about multiplicity / splitting. Yeah. Now, eventually, the HNMR and CNMR data, they're gonna get a little bit more complicated. Now, in Orgo 1, usually just by finding the number of signals, you could get the answer. In this case, it's gonna be a little more difficult. You're really gonna have to use chemical shift and concepts behind them, okay? Now, before we talk about that, let's do something that should be relatively simple, counting signals. So in this case, we're just gonna practice HNMR and CNMR. You have to tell me how many signals you see in each of those molecules. So I'm gonna give you about 10 minutes to do all of them. Let's see how many we can solve in 10 minutes. Because eventually you're gonna have to do this faster and faster. let's just start practicing. Give it your best shot. And if you have any questions, just raise your hand. Yeah, 5 more minutes. Did anyone finish already? Okay. For those of you who just finished, how was it? Hard, easy, so? Okay, I start going over them. If we don't have that much time left. But for molecule A in this case, the very first one. First of all, remember, number of signals is just the number of unique environments. So would symmetry affect it? Yes. Okay, now in that molecule, do we have any planes of symmetry?
Yes.
Right in the middle. Okay, now how many H and more signals do you guys need? What about C and more signals? 3, 4, 2. Actually, 4. Now let's go through each of them. Now, for H and M are pretty simple. We have the only methyl group. This is one signal. And we have the little lonely hydrogen right in the middle. Second signal. Now, why are those two hydrogens different from each other? The ones that are left over. Double bond, what do you say? Do they always come separately? What's the term that we use? Distereotopic. Now, let's just highlight them. These two guys are distereotopic. And don't worry, we're gonna talk about more about those terms later on. Okay, so it's okay if you don't fully remember those guys. In the middle? Yes, there's two, but they're gonna be two. That's why I hold you one. Now, same process for CN, yes,
I'm confused for the CMNR. Isn't there supposed to only be 3 there?
for CNMR?
Yeah.
Okay, let's go through that. So same process, method group, unique environment, right?
Right.
Now, second one, the first one that touches the double one. Okay, now, this one, keep in mind, it's connected to two R groups. But the other one that's far up there, double bond,
Oh,
hydrogens. So again, you have to look at everything, different connections, different environments. So those are 3, and then the very last one, the one right in the middle. That's 4. Mhm. Now, do we have any questions on molecule A? We're good? Do we see it? Okay. What about molecule B? First of all, do we have any planes of symmetry? How many? 1, and it's right in the middle. Okay. Now, how many H and M signals did you guys find? I heard a little whisper that said 5, I think, 5 as well. You guys are correct. 5 H and M. What about CNMR? 6. Now, same process. Yeah, remember, whenever you have any planes of symmetry, just look at one of those planes. That's it, because everything is gonna be repeated in every one of them. Now, same process. The ones in the method group, unique environment. Next one, the little baby hydrogen right in the middle, and you're gonna hear me saying baby hydrogen a lot for this chapter, because a lot of students tend to forget the ones that are right in the junction. Okay, so please don't forget those guys. They are there. Always draw out your hydrogens, especially at the beginning, when you're getting used to doing this faster and faster. Okay, now, this one, that one is really close to the method group, right? As compared to the one that's all the way in the bottom in here. That one's further away, that's why they're different signals. Let's just see. Okay, for CNMR, very simple. 1, 2, 3, 4, 5, and 6. You're basically just counting your carbons in one plane. That's it. The orange and the blue hydrogens. Could they be distereotopic? Do we use that term? Because they are part of a double bond technically. So. Would you call them distereotopic? Why not? In a way. So, okay, so distereotopic, it sounds like distereomers. What are some distereomers that you learned in Org 1? We have cis and trans. What are the other terms that I can call them? Cis. Now, in this case, aromatic compounds, they're not gonna be just in that form. Because of resonance, what we talked about earlier, they're gonna be moving around. So we're never gonna be able to create a certain distereomer. There's no E or C in here. Okay. Let's finish with molecule C in here. Do we have any planes of symmetry? How many? Exactly. Right in the middle and across from it. Okay, how many H and M signals do you see? We see 6 H and M signals. Okay, so those are very different answers. If you said 4, you're absolutely correct, but let's talk about that guy. First of all, main difference that we see between molecule C and A. Molecule C shows you stereochemistry. So keep in mind, whenever dashes, wedges, they're shown, remember that they are in different planes. Wedges, they're sticking out of the plane towards you. Dashes away from you. So that means that that's gonna cause a discrepancy between the distances. So different environments, so always keep that in mind. Now, in here. The little hydrogen right next to the oxygen, there's only one unique signal. Okay, little baby hydrogen, right there, second signal. Now, the next two hydrogens, why are they different from each other? They are cis entrants to the hydrogen, yes, or the alcohol group that you see there. So that's why this one, it's different. Whoops. And the dash one. Okay. Now, what about CNMR? How many signals do you see? Two. Only two. We only have 2 carbons per plane. Okay. Questions? Okay, we're good. We're good, we're good. We're good. Now, you guys, hopefully you're gonna see this today in lecture, if not, a little review from our one. And then we're gonna continue on, not Monday, Wednesday, Wednesday, remember the university is closed on Monday. So have a good weekend, everyone, relax, it's just the first week, so take it easy, guys, take it easy.